blocks which we can use it straight away into our program. So there are different signal generators, model and subsystems block, and this is how we make a typical block diagram and we operate it. So we'll be discussing the Simulink along with our biped model. Now I talk of actual control programming that will be required, and it is typically the part of the MATLAB or the basic control systems. So that before we move to the robot or biped robot applications, you can understand it in a better way, particularly for those who are not familiar with MATLAB. Those who are familiar, please excuse. So we write down the control system equations in state space representation. The force which we are applying is mv dot plus bv, and output is nothing but this variable v. So we can take a Laplace transform, and the transfer function is 1 upon ms plus b. And this denominator is also known as characteristic equation when we deal with it. So how do we translate this transfer function or utilize this transfer function in MATLAB? So MATLAB has a ready-made function which is known as TF. So this is generally used for a single input, single output. A robotic system manipulator or arm, generally whenever we talk of, it has multiple inputs and multiple outputs. So many joints are there simultaneously. So for each joint we have the input and the output also. So the transfer function model which we define as numerator and denominator. So whatever we talk of in the previous example, if you look at, numerator is 1 and denominator is ms plus b. In Laplace transform S domain we are talking of. So we can define this as a transfer function and numerator and denominator. And this numerator and denominator has to be specified in terms of the polynomial coefficients in descending power of s. So first we write the highest power term, and then we keep on doing on till the constant term. And if some coefficient is absent, that term will become 0. So as an example, if you look at 2s minus 3 by s plus 1, so this TF, the one written in red, is actually a MATLAB function. So we are defining this transfer function. First I have to define the numerator. So look at the coefficients 2 and minus 3. So highest power of s is 1. So first we are writing 2 and then we are writing minus 3. And in MATLAB, like I mentioned, either we can differentiate it by a comma or a space. So even if I write a comma here without any space, a comma will act as an element separator, or a space is identified by an element separator. And for denominator, the coefficient of s is 1 and the constant term is also 1. So we write this as 1, 1. So this is the complete denominator. There is a polynomial which we are representing with the help of coefficients, and MATLAB understands it. And this is the numerator coefficients. Similarly, another example, if you look at the second order term, 4s square plus s plus 1. So the coefficients will be 4, 1 and 1. This is how we define the transfer function in MATLAB. So output to input ratio. And a typical block diagram when we talk of, so we have the forward loop gain, we take some feedback, and this is a typical closed loop circuit block diagram which we follow for any controller. A feedback is required. So there we have a feedback function in the MATLAB, and we can define the forward path separately and backward path separately, and it will create the system on its own. This is the beauty of the MATLAB, or the advantage that we get when we are using the MATLAB. So we can use a closed loop transfer function and we need not do any computations manually. So I'm taking a forward loop given as 1 by STI and backward as V. So this is the proportionality constant, the amount of feedback that we are giving. So the transfer function is 1 by STI by 1 plus V into 1 by STI. 1 by STI is multiplied with this gain V. So we define first the transfer function, which is the numerator polynomials. So look at here. 1 first term, the second term is denominator. Okay. So the second term is denominator. The coefficient of s is ti, and there is no constant term. So when there is no constant term, this variable becomes 0. So we have ti and 0. And the denominator transfer function separately, because this is what the feedback command is. We have to define the forward path and the backward path. So in backward path, we are straight away defining this V and the I, the numerator and the denominator. So this is V, the numerator, the denominator part. So once we define this function or transfer function, It helps us in determining the step response. So this is exactly the same equation, 2s plus 1 upon 4s square plus s plus 1, which was there in the previous slide. Time is varying, so we have seen this operator. It will vary from 0 to 50 in steps of 0.1. And I'm determining this step response and the overall multiplication factor of 100. So this transfer function, overall transfer function which we have defined, this one, second one, is multiplied with a factor of 100, the overall gain. We can keep it 1 also, nothing else. So we get this as a typical response, the step response. And if you look at this, the value which we are looking into, the gain should be 100. So step response, final value will come out to be 100 only. And we have executed this program. Whenever we execute this program, what we can observe is these are standard parameters for any step response in control systems and even circuits and systems. So we have to reduce the amount of steady state error, which is the difference between the final value and the desired value. We have to reduce the amount of overshoot, the peak overshoot in comparison to the final value. The rise time, the time taken by the signal to reach from 10% to the 90% level, and the settling time. So within 2% of the final value. So ideal controller, we are trying to reduce or eliminate the steady state error. Overshoot should be as small as possible. And in manipulators, many exam applications, we have to avoid this overshoot that may cause a breakdown to an actual manipulator. Rise time, we want to be as small as possible. And settling time also, we want this to be as small as possible. So we talk of this controller example. So we know the standard reference input and the output, and the difference between the reference input and the output is nothing but the error. So on the basis of this error, we decide how much force or torque should be applied into an actual model. So we use this controllers, and controller will give us the amount of force or torque that is required. So E is representing the tracking error. So in robotics, we also talk of trajectory following controller that we'll be discussing in the Simulink example and MATLAB code also. E I have already told you. And the controller has to find out the derivative and integral. This is the mathematical block which has to do this. And U is the controller output which will be applied to the plant or to the robotic arm, and that will depend upon the error, proportional value, derivative value, and integral value. So this is the standard equation that we take as a controller output. So error multiplied with the proportional gain, the integral gain, integral term, and derivative gain with the derivative term. And its transfer function is this particular model. I'm talking only for the controller. Overall, the moment we add this integral term, it becomes a third order system. So generally we have seen this a very basic from control systems, because this is what we will be looking into the response. So Kp will reduce the rise time, but it will not eliminate the steady state error, proportional gain. The integral gain will help us in eliminating the steady state error, but it will decrease the transient response, or more time will be taken to reach the final value. Derivative controller will increase the stability, it will reduce the overshoot also, and it will improve the transient response also. So generally we use P and D more popularly in comparison to I in robotic applications. A typical spring mass system, a second order system. So ms square plus bs plus k, a typical second order single input, single output system. And we know if somebody disturbs it, it will oscillate and it will have a natural response corresponding to the spring stiffness value and the friction coefficient. Okay. Now we'll simulate it for some of the values so that you understand how we are changing the PID controller before we move to the actual robotic application. So the parameter values that we have taken is m is equal to 1 kg, b is equal to 10 Newton second per meter, and k is equal to 20 Newton per meter. And look at, in a MATLAB, I'm defining these variables m, b, and k for the spring mass system. Numerator is 1, denominator coefficients m, b, k, the transfer equation 1 upon ms square plus bs plus k. So m, b, and k. And we define the transfer function that we have discussed using the numerator and the denominator. And I find out the step response. So this is the step response for a typical spring mass system when it has been disturbed. Okay, so what we can find out is the steady state error. If you look at this value, the steady state error is very large. we are not reaching to the one value in this 2-second time. We are reaching only 0.05. Whereas if it is a step response, this graph should finally lead to value 1. The rise time is also more. It is around 1 second. The settling time is about 1.5 second. It is reaching here. So we use a typical PID controller to improve this step response or to get the desired response that we want as a controller. So those parameter terms that I was talking individually for PID are shown here with some example. And you can observe if we are increasing the value of P, how this response and the overshoot is increasing. So the rise time is improving, but the overshoot is increasing. So look at, there are many oscillations which sometimes may cause damage to the robotic arm also. If I use integral along with PI, so you can observe the steady state error in this curve and in this curve. So when I've increased the value of integral gain, the steady state error has reduced. Sorry. So this steady state error has reduced in comparison to this particular curve. If I use PI with different values and increase the value of I. So here the value of I is 500, 1300, 1320 and 1400. Now particularly the second, third and fourth graph, if you look at, the oscillations has started increasing. That's why it is recommended that the integral gain should be kept smaller. And this is with 1300. With 1320 sustained oscillations are there. And with 1400 the system becomes unstable. Oscillations will keep on increasing. So that is where the I value Ki should be small. And to compensate that, we add a derivative controller. So P and I we are keeping constant, P as 100, I as 200 in all these four curves. And now we have added the derivative control. So 2, 5, 10 and 20. So you can look at this overshoot is reducing as we are increasing the derivative gain. The rise time has also improved in comparison to the previous graphs. And that is what the transient response means. So we use a combination of PID. So if I use the optimal values and I can get a perfect response where if you look at somewhere between 0.3 to 0.4 second, we are moving to the settling value. Peak overshoot has reduced to a great extent. This overshoot is very small, almost negligible in this part. So these were the characteristics that we were discussing. What P, I and D does individually to these four parameters: rise time, overshoot, settling time and steady state error. So there's a classical control theory. I will go through it quickly. You are aware of it so that we can focus more on the MATLAB part. So when we add a P controller, the transfer function becomes Kp times here and Kp gets added to this K term. And this is what is used as a controller. So if I simulate that Kp value, I am setting 300. This is being set arbitrarily. You know, there are different methods to tune a PID controller. I'm using that feedback function available in the MATLAB. And for t is equal to 0 to 2 seconds, I'm determining the step response the way we have seen. And we can look at the rise time and steady state error has improved in comparison to what we have seen earlier, where the value was going only till 0.05 second, the very first curve that we saw here, this curve. So the value was going only till 0.05. This was the natural response. This curve also 0.05. But the moment we add a suitable P controller, we are reaching to the value of 1. Final value 1 is coming. Similarly, a derivative control has been added. So you can look at the transient response is improving. The overshoot has decreased. Settling time also comes faster. And we are using the same three functions: transfer function, the feedback and the step response. Rest is the simple way, the way we are defining in MATLAB, the way we have discussed. Then here I'm talking of PI. So this is the transfer function. Along with P, I'm using the integral control A. And this is what I was mentioning. The moment we add an integral controller, it becomes a third order system. So if we keep the value of Ki very small, effectively it will become a second order system. This Ki can be neglected in the numerator. This Ki can be neglected in the denominator. S term will get cancelled. And there is a separate field of research that works in reduced order modeling. So a third order system can be represented by a second order system. So rest everything else is same. We have put the Kp and Ki on the base of this numerator and the denominator equations, and we are simulating the same step response. And there's finally a combination of P, I and D. So I'm getting all three terms, derivative term, proportional term, integral term, both in the numerator and the denominator. And accordingly, this model is simulated. So you can look at the response that we are getting. Okay. So just what we have done till now is we are doing some manual tuning. We are changing some values and observing the result. Practically, it becomes very difficult mathematically to do it with paper or pen. So we have a better methods, Ziegler-Nicholas method and Cohen-Kuhn method. Of course, Cohen-Kuhn has a limitation that it works only for first order systems. So Ziegler-Nicholas is more popular. But with the help of MATLAB, we can quickly simulate, and we have the codes available even for these methods so that we can tune it and get the correct value of PID. So that is what we was looking into the manual tuning method. So it may appear very simple that change the value of P, I and D, but to get the actual correct combination, it is a challenging task. Like I was telling you, a very small change in the value of I resulted into an unstable system. So here the oscillations were reducing very slowly. Here it became a sustained oscillation, and here it became an unstable operation. So that is a challenge, and that is where we go into more mathematical methods to obtain the PID controller. Now we'll talk of an actual control that we use for a robotic application with this background of the MATLAB and basic control theory. So a typical robotic arm is represented by a system equation, is a second order differential equation, but it is coupled as well as non-linear. So I represent the number of joints. So EI double dot, KVI is the derivative control and P is the proportional control, and that is why it is multiplied with E dat. So standard control system representation, the dot indicates first order derivative, 2 dots second order derivative. So this is the actual robotic arm, which can be anything like this, actual model. Rest all is the controller part. And on the input side, we have theta d dot and theta d double dot. That is the desired trajectory. And on the basis of this error in the position and velocity, we are computing a torque which should be applied to the arm. And this is a typical computed torque model where we have the model based part which will cancel out all the non-linearities. And we have to select Kp and Kv so that we make these coupled equations as non-coupled. So I've seen the schedule. You must have done those dynamics and control theory in this workshop, so you can easily relate it with the computed torque model. So these are the parameters which have been taken from the book by Winter 1991, a typical human model which has been used for both the simulations in MATLAB and Simulink. So these are the different body parts: thigh, shank and foot. So thigh from hip joint to knee joint, shank from knee joint to ankle joint, and the foot part. And these are the standard length taken, each mass, center of mass of each of these components, and the moment of inertia. So these are standard parameters taken from this, and it is listed in the reference also in the last slide. So we will be continuously using these values for our simulation. Now I am showing an actual code for a computed torque control, and we will go it step by step so that all steps are followed. And this is related to this particular block diagram only, where we have a desired trajectory which a robot should follow. We have the inertia matrix. So if it is 7 joints, this will be 7 cross 7. And we have the non-linear terms where this V theta theta dot represents the gravity and the Coriolis and the centrifugal term. G of theta represents the gravity term. And this F theta theta dot is the frictional term, which when we do not model it, so actual model is written here, M theta theta dot, V theta theta dot, and G of theta. So inertial term, Coriolis and centrifugal term, and the gravity term. So this friction acts as a disturbance, and we test it with the simulation that even in presence of disturbance, the trajectory is followed. So that is what we'll be doing in this code. So initially the output, I'm defining everything as 0. So x1 to x7 and their dot values. So initial values are 0. That is position and velocity. Initial value is 0. We are using an ODE23. There's a MATLAB function, ordinary differential equation solver, and 2, 3 corresponds to the Ranga-Kutta second order method that is used for integrals and solving it. So two functions are written. One is to do an actual computed torque calculation. Right from T0 to TF starting to final value, I am simulating it for 1 second, 1 step cycle. Initial values, I am putting it all 0, position and velocity for all the joints. So it will be a 7 joint biped model that we are discussing. Once we have obtained the solution for X, the actual values, I find out the error. And for that, I have written a different function. So where QD is the desired value and X is the actual value that we have found out after applying our computed torque. So the difference between them. And these are some of the commands which I have listed. Plot is known to you. It will plot. T is the independent variable and E is the dependent variable. That is, T will be plotted on x-axis and E will be plotted on y-axis. And since there are 7 joints, we will get 7 values here. So that is what we are taking. First column represents error for joint 1. All rows by default. This column indicates by default all rows. Second column, third column for each of the joints. So we can plot it separately and observe it. Now we'll see what we actually do in the computed torque. So the first function that we are calling here was degree of freedom for robotic computed torque 7. That function is like this. We are defining all the parameters that we have taken from the biomechanics books by Winter 1991. Gravity and Kp and Kv, these were some values written initially, which we can tune. Now this theta trajectory which has been generated is also taken from the Winter reference only, and this is a 5th order polynomial, and these are the coefficients of the polynomial, and we will be using the function polyval to evaluate it to generate the trajectory. So we are writing the coefficients. So if you observe, this is A5 T5, so A5 A4 A3 A2 A1 A0 constant term. So these are the coefficients for the 7 degree of freedom. Theta 4 is for the torso part, and which more or less we have kept it as constant. So at 10 degree, the torso is being represented. Polydir is again a MATLAB function which finds out the derivative. So it takes the order from this term. This is t to the power 5. So it will automatically take it as 5a5t4. So 5 times this it will store. So after taking the derivative, one order of the polynomial will reduce. So it will be a 4th order polynomial. So we are taking the derivative for all these positions. So I get the velocity. Similarly, I take the derivative of the derivative, that is 2nd order derivative. So I get the acceleration. These are the values because those values were in radians. So we are converting it into radians. So all those position values are being converted into radians and evaluated. This is the MATLAB function polyval, where we can specify the coefficients and it will find out the value at all values of t. And theta 1 is a polynomial coefficient that we have already defined. So we are calculating all the position, the velocity and the acceleration. So position, velocity and acceleration. So with MATLAB, we need not find out the derivative separately. There is a function available. The only thing is we have to add order or input the coefficients. Then for the computed torque function, the position QD for all the 7 joints, the velocity, I'm taking the derivative, and the acceleration. So these are the desired values for position, velocity and acceleration. And error is taken as the desired value minus the actual value. So x1 to x7, this gives me the error in position, and x8 to x14 gives me the error in the velocity. So 8 is the derivative of first joint, 9 is the derivative of second, and so on. So we are finding out the error that we have to plot. Now these are the typical components where simple mathematical operation is being done. So you must have seen those dynamics, LE formulation and NE formulation, the two popular methods. And we are calculating each of these inertia terms, which is a 7 cross 7 matrix. So all 7 cross 7 elements which are being calculated. Then I'm calculating the non-linear terms, that is the centrifugal term and the Coriolis term. So those are again 7 cross 7 matrices, 7 cross 1. And then I apply the actual control theory. So I'm using proportional plus derivative here in the computed torque. So this is the desired value, acceleration, multiplied with the error in the position, derivative part, and error in the velocity, and this is the error in the position. So proportional gain and the derivative gain. So we are multiplying it. Kp is the proportional gain, Kv is the derivative gain, to obtain the state of the system S1 to S7, in which state it should be. So please make a note here. This theta double dot is the desired value, and these are the differences from the actual value desired value minus the actual value. And then I'm calculating the torque. So we are having the inertia component multiplied with the acceleration term and all nonlinear terms combined together. So since a robotic is a highly coupled system, you can observe here this torque 1 is dependent upon state of joint 1, state of joint 2, state of joint 3 and all 7 joints. That is tau 1 is dependent on position, velocity and acceleration of all 7 joints. Similarly, it is true for all. Tau is the torque symbol that I have used. So this is the moment of inertia matrix, which has been formed here as D, because we need to calculate the inverse. So it is a 7 cross 7 matrix. And in MATLAB, we can easily find out the inverse using this function INV. So inverse of D is calculated using the MATLAB function. So it does the computations and gives us the result. So look at x dot 1 to 7, the control theory. So we are representing it with x8, 9, 10, that is the velocity state into x dot 1, x dot 2 and x dot 7, that is the velocity of each of those joints is assigned to these variable. And this is what we have to return into the main program. So we calculate from that x dot 8, 9, 10, 11, 12 and 13. Okay, that is the new values of the velocity for the joints, all 7 joints. And then we assign this x dot as the transpose of this x dot. That is, we are assigning the new value for the new time interval, which has to be returned to the main program. So in MATLAB, you can write the functions also. So if you look at this is a function x dot, that is the value returned will be x dot. The function name is DOF ROBCT7 and the input parameters are time and the x, and it will return x dot, and that is what we are computing at the end as x dot. So from 1 to 7 and then from 8 to 14, and this we are returning it. Now the second function which we have used is to plot the actual output so that we can observe. So this is the desired trajectory theta 1 to theta 7. We are evaluating those polynomials. And look at the desired trajectory theta 1 to theta 7, and the error is nothing but QD minus actual values of x. And we are using only first 7 columns because column number 8 to 14 is for the velocity. So we are finding out the error in the position here. So I will show the graph combined together. It's almost similar, but this is how it works, a computed torque control in a MATLAB programming environment. Now we move on to Simulink, and it is a software package which can be used for modeling, simulating as well as analysis. It supports both linear and non-linear systems, continuous as well as discrete. Those who have done advanced course in control theory, they know a lot of differences comes when we implement it as a discrete or a digital control. It supports multi-rate also. We can model the real life situations. I will show you the biped model example. And it supports both top down as well as bottom up approach. That is, we can follow a modular approach and write different modules. So what Simulink is used for is, it is used to create a block diagram or model, and then we can represent that system and simulate it with the block diagram itself. So this is a typical environment of a Simulink. You can find out the library here. We'll be going through it, these functions, what a brief is required. And this is the kind of model that we build using the functions available in the library. And we can simulate this. If you find out the simulation tab is there, we can simulate it. And there are various models and subsystems which are readily available, and we can create our own systems also. So this is a typical Simulink screen when you operate in MATLAB, and is simply at MATLAB command prompt, you can write Simulink all in small, and the Simulink tab will open. So this is some of the screenshots which I have put. So Simulink has various functions. From this point onward, these are the different toolboxes that comes whatever license you have. But look at this one, important is the source. So source is where we are giving the input. So we can have different kind of signals which are available here. We can have a digital clock, we can have a clock, we can have a chirp signal, we can define our own signal, the pulse generator, even the function generator is available. So various kind of signals that we need to give input is available in the source block. Then we have a sync block. So where it terminates. So basically we can use an oscilloscope to observe those graphs. We can have an XY plotter graph. We can have a simulation output model. We can simulate it to a file, that is get the output data in a MATLAB file and store it, or even an Excel file. And we can have a LCD display arrangement. So these are the sync where we can observe the output. Then the commonly used blocks which we'll be talking of is, we have a data type conversion from one data type to another data type. The delay, the demultiplexer and multiplexer, this will be used in our model also. We have two inputs and we are taking a product. Mathematically, if I have to multiply two functions, we can switch from one input to another input. And this is a complete subsystem like a function. We write function in any code. Similarly, we can create a subsystem and everything will be hidden inside it, a black box, some input and some output. So these are some commonly used blocks, and this will vary from your various versions and the way you use it in a MATLAB. And continuous, some of the blocks that we will be using is, look at this 1 by s. So it is represented in Laplace transform. 1 by s is nothing but integrator. So we'll be requiring this integrator. Du by dt is nothing but derivative. So we'll be requiring this derivative when we have to do the computer talk and PID control that we have to implement. So you can pick up the functions. It is drag and drop and connecting. This arrow you can connect. This is the input, and this output tab you can connect to another block in Simulink. So what we'll be talking of is, with the trajectory as an input, we will have a controller and an actual robot. And this is one leg model. So some angles θ1, θ2 and θ3. And if you look into this model, the angles are measured with respect to the previous joint. So these are basically flexion or extension angles. And in our model, we convert it with respect to the vertical. So this is the second figure. So we need to convert these angles. Like if you look at this θ3, it is 90 degree plus this angle θ3. That is how the flexion angle comes. So we'll be doing all this in the Simulink model, which I will be showing you for a 7 degree of freedom. So this is shown for one leg, similarly second leg and the torso part. Now this is an actual Simulink model. So look at here, we are having the trajectory. So hip joint left, knee joint left, ankle joint left, and these are the right joints, and torso we have kept it fixed. And this is my own signal generator. So I have generated gate cycles in this block, the same polynomials that we have seen in the computer torque model in MATLAB environment. Then I'm converting the angles here, like the flexion angles, to be converted into the angles from the vertical reference. This is the conversion from degree to radians. And then I have a controller block and an actual robotic model. So input is torque and output is angles. And here I have plotted various oscilloscopes so that I can check the references, the errors, the controller output and the actual output. And here I have generated a Simulink model where we can even visualize how the biped is walking. This was a GUI interface. So right now I will not be able to run it because it needs an actual MATLAB license, and I'm working from remote right now. So today I'm not in campus. So I will not be able to demonstrate, but I will show you the screenshot. Now I'm going inside the block. Look at this is the subsystem. So inside this block I'm doing is I'm doing the angle conversion. These are the blocks: angle conversion block, controller block, gate cycle builder, graphs, and the Simulink dynamic model. Now I'm going inside the block. So for joint 1, it was measured with vertical axis only. Look at joint 1 was measured with vertical axis only. So no change is required. So this is as it is, and this is nothing but the multiplexer block that I have shown you in commonly used blocks in Simulink library. For link 2, I have to add this first angle and subtract the second angle from it so that I get the angle from vertical. And in the third one, I have to add a 90°, and that is what I was showing in this particular diagram. So this 90° has to be added so that I get the angle from the vertical. So this is the block typically that we are doing. And look at, there are 6 inputs and 1 output. So this is a multiplexer, and this is how each output is connected here. Now this is the controller block. So PID control block is available in control toolbox in Simulink. And I can straight away set the value of P, I, and D from this part. And to test whether it works in presence of disturbance or not, I have added a disturbance noise also. And this was a Gaussian distribution which has been added here. So we are giving the error to each of these joints. And with the help of PID controller, we are generating the torque. And this is the disturbing torque that has been added as a standard control practice to check whether it will work in presence of disturbance or not. So the ease that Simulink gives is I need not write any code. Simply I click on this PID and I can set the value of P, I, and D. So look at, I've set the value 200, 0, 200. This was something arbitrarily that has been done. And when we mask it, only the first block is visible to us as a black box, but this is what is present inside it. And this is the transfer function that we were talking of, P plus I by S plus DS, PID controller. Now this is the actual Simulink model. So when we are applying the torque that we are getting from the controller to a robotic arm. So in real life, there will be a robotic arm, and in Simulink, we are simulating it. So we need a mathematical model. Look at this block diagram that we have at the beginning. This one. So this robot can be an actual arm. In Simulink right now, it has been simulated with the dynamics equation. So each leg a different model, left leg and the right leg. And if you look at, I've set those parameters that are taken from winter biomechanics books inside this. And I will show you inside this leg model also. So when we mask the system, I can simply input the parameters, double click it. I can change the mask very easily here in a GUI based model itself. And this is one leg model. If you look at, so complete torque calculation is being done here. And look at, when I'm taking some product, some multiplication with a constant, this 1 by S will integrate it, and 1 by S another integration. So if I get theta double dot, this will be theta dot and this will be theta. So this 1 by S block is nothing but the integrator. We are taking some product, some addition here, complete function, the complete mathematical expression for the torque can be written here. And this has to be fed back to the input. So whatever is the actual value, this we are giving it back into the dynamic model of the leg so that the error can be computed. So using each of these, this is a function block available in Simulink where you can write your own variables, and U is the input. There can be multiple inputs also, and U index 1, U index 2 will be used to represent those various inputs. A difference block, plus and minus, both plus means it is an adder block, a simple product of these two terms. I am multiplying it with a constant here. It can be any function also here. And then these are the integrators that we have used. These were the typical error plots. I've used 6 oscilloscopes for all the joints. So these are the actual desired values. These are the error at individual joints, controller output at all these joints, and the actual output that we are getting. So it is basically just to observe. I've used it. Otherwise, we know this reference minus actual gives me nothing but the error. So this is some of the reference plot that are being shown here for hip joint, knee joint, and ankle joint. So all 6 curves. These were the input values. And this is the error model. Now look at when we are running it for 30 seconds, somewhere around 4 seconds, all these errors become very small. And after that, you can observe the error is almost negligible. That means the PID controller works perfectly fine and we can deploy it for an actual biped robot model. And this was the actual simulation, which unfortunately I cannot run today. But this is how the joints will actually move and it will actually show. So this is taken at a particular instant, how it will be moving. And this is the actual figure that has been taken from the Simulink. And this is only this part which has been demonstrated here. So you can observe the joint positions at this way, and this will demonstrate the actual model. Of course, this will take you some time to understand the MATLAB and write the GUI model. But up to this graphical curve, it is very easy. The more you experiment, the more you learn in the MATLAB. So these were the typical references that has been used. Mainly MATLAB I have used for all the simulation work. We have taken the data from the winter for the trajectory as well as the parameters that we have used for the simulation, and a typical control theory book that we are done with. So I am done with the actual control and hope you can understand and follow it and start implementing some basic MATLAB codes or Simulink. You can start using it. But I am available. If you have any queries, please go ahead with it. And thank you very much for listening this talk. Thank you. If there are any queries, you can ask me.
How will we get the dynamic model?
Dynamic model in MATLAB or Simulink?
No, actually, which so it is 7 degree of freedom.
Yeah.
So how this model was arrived at for simulation?
Okay, so the model, the dynamic model comes from the LE formulation or the NE formulation.
Okay, sir, it was readily available. Or
No, it has to be derived. It is not readily available. Those equations have to be derived, and of course, you can find out some research papers where it is available, but this has to be derived because each arrangement will be different. So for each robotic arm, it has to be derived, whatever degree of freedom you are using, using the standard techniques, Lagrange-Euler formulation or Newton-Euler formulation.
Okay, thank you, sir.
So if there is any other query, the time allotted to me was somewhere between 45 minutes to 1 hour. So I'm exactly into the middle of it. If there are any queries, I will be happy to take it.
Thank you, Professor Rai, for such an informative session. I hope participants must have learned a lot during your session how to use MATLAB for robot control. Thanks, Professor Rai, for giving us your valuable time in spite of your busy schedule. Thank you so much.
Thank you very much, sir. And with your due permission, I will be leaving this meeting after this. Am I?
Okay. Yes.
Okay.
Yes.
Yeah. Thank you very much, sir. Thank you.
Thank you. So now the next session is on the application of microcontroller programming for robotic application by Dr. Mr. Sajal Babu Daniel. Currently, Sajal Babu is pursuing his PhD at MNNIT Allahabad, but he is the key person involved in the uh, development of most of the devices at our biomedical engineering. So you can say he has made our biomedical engineering laboratory by hand nowadays. So I will give a brief introduction about Mr. Sajal Babu. He did his BTech from IITS, Robotics, then MTech in biomedical engineering from MNNIT Allahabad, and he was after that he was a guest faculty at MNNIT Allahabad. Now he is pursuing PhD from MNNIT Allahabad, and his area of interest are assistive medical devices, IoT-based medical devices, sensors and actuators, and he is working a lot recently. He has developed an thermal scanner, that is IoT thermal scanner, which can get directly reading of the temperature of the cloth from a distant place on the mobile based at some distant location, and the reading data will be stored across government or further channels. So, and we are going to file a patent, and the whole credit goes to Mr. Sajal Babu, who is behind that project. So now I would invite Mr. Sajal Babu for his talk on Microsoft programming for robotics. Mr. Sajal.
Thank you, sir. So, is my slide visible, sir?
Your slide is visible. Sajal, your slide is visible.
Okay.
Yes.
Okay, thank you, sir. So, thank you, sir, for introducing me. So, today I'm going to make you learn about how to program a controller here. So, as many of our experts has gone through many types of controllers and they have sent many control strategies, everything. So today we will discuss one of the controller and mostly used controller in most of the prototyping devices. So if anyone is having any problem in my, or if there is no clear voice or if my slides are not visible, please let me know. So today I am going to introduce you to the Arduino board. I think many of you had know this board and many of you are also worked on this board. Whenever we are going to discuss about the robotics, so it is one of the important thing to learn about the Arduino board because it is one of the easiest IoT based, you can call it as a prototyping device, which we normally use in prototyping at in our project, especially at prototyping levels. So let us start with the Arduino board and then I will make you learn how to program this Arduino board, and then I will show some of our projects, how we have done that and how the coding has been done for that. I will show you everything of that. So before going into the project that we had done, so I am going to explain this Arduino board. Many of you may know, but try to go through it again so that it will be easy, and I will explain it in an easy way so that every person can easily program it. Okay, so you can see on the screen, this is the Arduino board. The board I am showing you on the screen is an Arduino Uno board. So coming on to the parts, I am just going to the parts of the Arduino board because whatever maybe you are doing, maybe you are using the Arduino board, or it may be a Raspberry Pi or any controller, whatever the controller you are going to use. The important thing that we need to learn is what are the pins that we are having with that board. So coming on to the Arduino board, so you can see here, 1 minute. So you can see here, this can be directly programmed by using an cable, you can call it as a communication cable, which is connected to our USB port, and it will be considered as one of the communication device. If you have installed the Arduino IDE software properly in your system, then your system is going to recognize this Arduino board as an communication device, that will be the name of the board, like Arduino Uno or Arduino Nano. So I will show you how we are going to install the Arduino IDE software, where we are going to write the code and where we are going to upload that in our Arduino board. So this so let us see the construction of this board, because this will give a very good idea. If you know about the board, it will be very easy for you to interface any sensor with this board. So this is a USB plug where you are going to use this plug to plug your board with your system. It may be a laptop or a computer or a desktop, and then you are going to have an external power supply, and this a particular external power supply which you can see here. So this external power supply can be used when your programming part is completed and you are going to implement it in real time. So there you can power this complete Arduino board with an 9 to 12 volt supply. So you may use a battery or you may use a cell, whatever you want. So and then you can see here this one as I represent it here. So Atmega 328 P. Actually, it is a P. It is not mentioned here. So normally the Arduino board, whatever the Arduino board you are going to get, I will show you the different types of Arduino board in the next slide. So whatever the Arduino boards, it may be Atmega, Arduino Uno, Arduino Nano, whatever the boards you are going to use, you are going to have this controller as one of the important part. So if you go through the Arduino tutorials also, most of the people say that this board, this complete Arduino board is going to have only one microcontroller, and that is Atmega 328P. But it is right up to that, it is going to have a Atmega 328P microcontroller, and which is an important part of the Arduino board, and this is going to execute the code that you are going to run here. But apart from that, here you can see another IC. You can see here the small chip. This is also another controller. This is an Atmega 16U. So never think that the Arduino board is going to have only one IC. It is going to have two. One will be acting as a main, other one is here. You can see Atmega 16U. This is known as an USB debugging. So I will explain you some. Some of you may think that it is going to the coding part. No, but you have to learn this. Like why the Atmega 16U controller, which is a USB debugger, is using here. So whatever code you are writing here and whatever code you are going to upload in the Arduino board, so it will not be able to understood by this controller. So this debugger is going to convert the code from a wide language to a machine language, and then going to upload it into the Arduino board. And then it is, and remember one thing that if you see in many of the tutorials, most of the people say that the Arduino will have different baud rates like 9600 or 15200 or many 4800. They used to say that this Arduino board may work at different baud rates. It's right up to some instance, but you can see here we are having an one component, and this is known as our crystal oscillator. So whatever the program the Arduino board is going to execute, or whatever it is going to run in a real time, so this should require clock pulse, and that particular clock pulse will be provided by this oscillator. So it is a 16 megahertz oscillator, and if you want to utilize this Arduino board at more effectively, then we suggest that you have to use it at 9600 baud rate. So 9600 will be a perfect baud rate by this Arduino board. It may work at higher or lower baud rate, but you are not going to utilize the board completely, and sometimes you may get some errors with that. So try to use the Arduino board whenever I think most of we here are faculty members. So if your students are using the Arduino board, or try to prefer them to use the Arduino board for 9600 baud rate. And if it needs not that if your application requires an 115200, that means baud rate, that means higher baud rate. So there may be other boards which can work at higher baud rate. So and then these are the you can see here I have written is that insert to serial programmer, and these are used for programming. If you have removed this particular long IC, which is called as an Atmega 328P, then if you are and if you have erased the bootloader, remember one thing. So what happens with the Arduino board is this particular Arduino board here we are having, so it is going to have some bootloader with it, like we are having a Windows OS or Mac OS or Android OS. So similarly they may have their own bootloaders, right? So similarly this particular Arduino board, normally we can write the code in Java, C, C++, and whatever code you know, whatever the computer language you know. But this is this controller majorly this is going to have its own bootloader, which is known as an Arduino bootloader. So if you have corrupted this bootloader, then you need these pins, ICSP pins, for reprogramming or reinstalling the bootloader. And then let us read the other part of this Arduino board. This is a reset button, and then this is a comparator here. So these are other things, but the important thing that we have to learn here is the pins. So the Arduino board, the reason why this board has been most popular is because of its easy use. Because if you are having an analog controller, analog sensor, or if you are having a digital sensor, or if you are having any other sensor, so you can easily interface the sensor with this Arduino board. So you can see on the this part, so as I have written here, analog input pins. So like whatever the sensor you are going to take, whatever sensor you are picking for your application, so it is not compulsory that your sensor may be a digital sensor. So sometimes your sensors may be also an analog sensor which are going to read some data, and then it is going to convert that into an analog value. So the analog pins, there you can use these analog pins directly on the Arduino board. So you can connect the analog sensor directly on this A0 to A5 pins, and then this analog sensor, after connecting the sensor to these pins, so this Arduino board is going to have its own ADC, which is called as an analog to digital converter, which will convert the analog data into digital, and then it will give the data to a controller. So there you don't need any ADC if you are using this Arduino board. And then here you are having an 13 pins which are called as an digital pins. So these digital pins normally they have here it has 0 to 13, but if your application is having more sensors, then you may also use the 0th one first pin. But the problem that you are going to get here is whenever you are going to upload the code into the Arduino board, so these TX and RX pins may get disabled at that time. So that's the reason why most of the people will prefer the pins from 2 to 13, but actually you can use the pins from 0 to 13. So you can connect any digital sensor or any digital actuator to this 0 to 13 pins. And the other important pins that we are having here, I have said we are having analog pins and we are having the digital pins apart from analog and digital pins. So you can see here some of the pins we are having, like the third pin here, or the fifth pin, the sixth pin, 10, 9, 10, 11. So you can see a sign symbol in front of these pins. So these sign symbol represent that these pins can be used as PWM pins. So like sometimes in some of the application we require a PWM signal for our controller. I will show you in our one of the experiment that we have done in the lab. There we are using the PWM pin of the Arduino board. I will show you that in our later slides. So if your application requires a PWM pin, there you can use these PWM pins here. And then apart from that, your Arduino is also going to have some power pins. Like let us consider you are having an sensor. So that sensor is going to have 3 pins. Whatever the sensor you are going to take, that sensor, I am saying it in a broad way. So whatever the sensor, I am taking a block here. So whatever the sensor I am going to take, this sensor is going to have 3 pins. So one will be VCC, other will be ground, and other will be called as a signal pin. So depending upon the sensor and depending upon the type of communication it is going to do, the signal pins may be not 1, it may be 2, 3, it may be 2 or it may be 4. But if you are considering all the sensors at a time, so if you can see, if you are having a sensor, the sensor is going to have 2 power pins and 1 signal pins. That means this sensor needs some power supply for its operation. That means for doing any sensing, it needs some power supply, right? So the Arduino board is capable of giving 5 volts or 3.3 volts supply, but remember that you have to connect only those sensors which are going to have a current rating below 100 milliamps, because this Arduino board is not capable of providing power supply for some sensors which are going to take current more than 100 milliamps. So remember that if you are using the pins, inbuilt pins of this Arduino, that means that 5 volts pin or with 3.3 volts pin, try to consider that you have to connect the sensors which are having a current rating below 100 milliamps. Otherwise your board is going to not the board is going to do anything. You are going to connect this board to your USB port, so definitely your USB port is going to get burned out. So remember that the Arduino is capable of giving the supply only 100 milliamps. But if you are using any motor, there you need to use some external power supply, and I will show you how we are going to connect the motors which are having high power ratings. Because the Arduino board is going to operate at a low power supply. So if you are having a motor, like I will show you the wheelchair application where we are using this board. So at that application we are having a PMDC motors. So they are going to have a current rating of 10 amps and 15 amps. So at that time also this Arduino is going to control those motors, but how I will show you in the coming on slides. So this is about the Arduino board. I just give a brief introduction because many of you know about this board. So coming on to the next slide. So the Arduino, is not a single board of the Arduino. And remember one thing, the Arduino IDE software, which is a uploading software or integrated development environment. So it is an open source. Anyone can download from the Arduino IDE, Arduino.cc website, and they can install it. You have to just purchase the board. Now, in India now we can get the boards at a very low cost, below 500 also. So if your application is having, or if you want to design a project at a very low cost, then you can prefer these Arduino boards. I'm just going to show you how many types of Arduino boards that are available that we can use here. So this is the Arduino which is most widely used. This is Arduino Leonardo, and then this is Arduino Mega. So you can prefer the Arduino Mega if you want to control more number of appliances. And then this is Arduino Lillipod, and then Arduino Mega, Arduino Fio, Arduino Ethernet. If you want to do some IoT, if you want to do something with internet, if you want to upload some data from the Arduino to the internet, then you can prefer the Arduino Ethernet. And this is Arduino Pro, and then Arduino BT. So if your application needs a Bluetooth module, and you definitely need some Bluetooth module, then you can go to the BT, and Arduino Nano, Arduino Mini, and Arduino Pro Mini. So these are the different Arduino boards. Apart from that, you can also use the Raspberry Pi and many other Raspberry Pi. There are different versions in Raspberry Pi starting from 0 to 3B plus. So you can use any of that. It depends upon complete your application. If you want a GUI, because the Arduino, the Arduinos are not going to have any GUI. If you want a graphical user interface, or if you want to have a OS install, like if you want to install a Linux OS, or if you want to install a particular Windows OS in your particular controller, then I will recommend you to go for Raspberry Pi. And depending upon how heavy software you are going to run, what is the application, you can choose the RAM configuration in the Raspberry Pi. But if you don't need the GUI, and if you want to just use it as a controller, then you can easily go for the Arduino board, which is an easy part for your project. But I want to suggest you, because I had done many prototypes with these Arduino boards. So whenever you are going to purchase this Nano, that's the small one, which is very small board, try to purchase it original. If you are going to purchase a duplicate version of it, because you are going to get each and every board a Chinese version of these boards, if the original version will be from Italy. If you are going to purchase their cheapest boards, then you have to use the drivers apart from the drivers that you are going to get with the Arduino IDE boards. So just try to remember that if you are normally, if you are going to purchase other boards at a low cost, then you are not going to get any issues. But if you are going to purchase Nano at a low cost, then you are going to get issues with the drivers. Your PC will not able to detect this Nano. So try to consider it. So, and then this is about the Arduino boards. And then coming on to the programming part. So for programming Arduino board, so we are going to use an Arduino IDE, which is called as an integrated development environment. So this particular interface will be used for writing the program. You can write the program here itself, and then you can upload the program directly into an Arduino board, what you are going to have here. So I will stop the slide here, and I will show you the actual Arduino board. I will show you the actual Arduino IDE software, and I will explain from there so that you can easily get it. So just 1 second. Just 1 second. I will share the ID with you. So I think you people can see here on the screen, this is the Arduino IDE. I had written some code here. I will explain this code later on. So I will definitely explain it. So you can see here, this is the interface which you are where you are going to the IDE software, where you are going to write the code for your Arduino board. Remember one thing, whatever the board you are using, I have shown you many different types of Arduino boards. So whatever the boards you are going to have, you can you can write the code here itself. For all the boards, the coding will be same. If you are taking any board from Arduino family, so the coding will be same for all of them. Just you have to keep in mind that you have to consider the baud rate depending upon your application. So this is the Arduino IDE software. So this is the space where you can write. This is called as a space where you can write your Arduino code. You can use C, C++, Java, whatever the coding language you know. But you have to use the wide library here, because it is an Arduino IDE software, so you have to use the wide library, which is called WAID wide, which is called as a wide library here. So you are going to have some basic functions. I will explain you some part so that you can easily code in your next coming on projects. So let us see what are the options that you are going to have in this Arduino IDE software. So first here you are having a file. In this file, when you are going to click on the new, so you are going to get some new window there, and then so using the open all this you can know, and here you are having an examples tab. So if you are new for the Arduino IDE, if you are using for new for it, you can go through these examples. You are having different examples, you can go through it and you can run it so that you can get in touch with the Arduino board. And then coming on to the edit here, so on the edit tab you are going to have copy to forum, copy as HTML. So you are having some options like copy to forum. So why the copy to forum option is available in the Arduino IDE is if you have written some code and you are getting stuck at any one place, and if you need some help, so just click on the copy to forum. 1 minute. Just click on the copy to forum, and then you are going to have an Arduino forums, or you can also upload it and stay other forums where there are many forums for Arduino help. So there you can paste this code and you can get the help from the experts or the persons who have already done the Arduino programmings. And then coming on to the sketch, so here you are going to have the upload all these things, and apart from that here you are having an include library option here. So why this include library? So whenever you are going to use the Arduino board, the first important thing that you need to consider is the sensor, whatever the sensor or whatever the module that you are using with the Arduino board. Is that particular sensor or module requires any library? Because like if you are using a temperature sensor, which is called with a draw name of DHT11, humidity and temperature sensor, or if you are using some other sensor like IR sensor, or if you are using an, let us consider the basic HC05, which is called as an ultrasonic sensor. So if you're using these sensors, so these, if you want to like HC05 sensor, let us consider HC05 ultrasonic sensor. So if you're using a HC05 ultrasonic sensor, so whenever if you what the ultrasonic sensor using going to do there, it is going to first emit the ultrasonic waves. The waves will get strike with any object, and then the wave will get back as an echo, and the echo the sensor is going to receive the echo and you are going to calculate the time. So for this complete operation you need to write a big lengthy code, right? But in the Arduino, if you there will be a library option. So like in the include library, you can go into the manage library option here. So you can click on the manage library and you are going to get a search box there, and from the search box you just type the HC05. Try to type sorry, try to type the exact name of the ultrasonic sensor or whatever the sensor you are using. If you are using ultrasonic sensor, normally HC05 will be the ultrasonic sensor. Sorry, okay, so it will be you can type the name there and you can get it there. Okay, so you can type the sensor name and then you can download the library. Once you download the library, you just need to include your library, like include library name there, and the library will get included, and then you can directly use the function which is defined in the library there. So some of the libraries will be available in the Arduino manage library option, and if you consider you are using a sensor and that particular sensor's library is not available in the manage library, that means library manager of this Arduino IDE, then but you can get the sensors, like I will let you know that if you are not having a particular library in the Arduino IDE, you can directly go to the GitHub, and from the GitHub you can download the zip file of the library, and then you can directly add that zip file in the Arduino IDE software here. So at the second option here you are having an add.zip file. So just click on the add.zip library here. So when you click on the zip, then it will give a window for browsing. Just browse the zip file and upload it. So the library will get included in the Arduino IDE software, and then you can use the library there. And then coming on to the tools. So this is the important part of your Arduino board. So I think you can see the tools menu here. So coming on to the tools. So here you have to select the board, which board you are going to use here. At present, I am not having the Arduino board with me. So which type of board you are going to have? First, you have to connect the board using the cable, and after connecting the board with the cable, you have to select the board. What is the board you have connected? Normally, the Arduino, the lab, if you have installed the Arduino IDE successfully, so it is going to detect automatically. If it doesn't detect, just go to the board here in the tools. Just go to the board here, and in the boards you are going to have different boards. Select the board that you are having, like Arduino Uno, Arduino Nano, whatever the board you are connected. Select the board, and then under the port option here you can see I have not connected the board. That's why I am getting the COM3 option here. If you are connected the board is going to the system is going to allot a particular COM port for that board, like COM6, COM7, or COM8. So it will come here like COM8 in the bracket Arduino Uno. Click on that and then just write the code and then you can upload it. So this is the two parts, and I will give you a trick if you are using a nano, because nowadays most of the people are interested in making your prototype in a very small compact way, right? So at that application most of them use Arduino Nano. So I will give you a trick. If you are using Arduino Nano, it is not getting uploaded. Whenever you are going to upload the code, it is giving some error. So what you need to do is just go to the, just I will show you, like select the Arduino Nano. After selecting the Arduino Nano, here you are having a processor option. This will come only for Arduino Nano. Once you select in the board, once you select Arduino Nano, go to the processor. If you are purchased an low cost Arduino Nano, just go to the second option, Atmega 328p old bootloader. Then upload it. You will not get the issues of uploading errors with the low cost Arduino boards, because in the low cost Arduino boards they are using the I am especially saying this for Arduino Nano. So there you can select the old bootloader and you can upload the code there. So these are the some of the important menus that you need for writing and uploading the program into the Arduino board. And then here you can see a tick mark. So this tick mark is for compiling or verifying. So you have written a low code, right? I have written a big code here. I will click on this tick mark. So what the Arduino IDE will do, it will check whether is there any syntax errors. If you are using any particular function has not defined, or you have not used any particular function of Arduino IDE, then it will check it. And once if your complete code that you have written here is right, then you will see here at the bottom, you can see done compiling. So this will be done compiling option will be shown here. And then you need to click on the upload. Once you click on the upload button, this complete code is going to get uploaded in your Arduino IDEs, or sorry, Arduino Nano or Arduino Uno board, whatever the board you are going to take there. And then you are having the save and the, so you have to save the, if you want to save it, you can save it. So this is the part of the Arduino IDE software. Before going to code the Arduino Uno, I had explained you the Arduino board and then Arduino IDE software. And as the time is less, so I am just giving a brief, which will be sufficient for you for doing your prototypes. And so this is the Arduino board and Arduino IDE software. So let us move into the coding part. So 1 minute, I will share this. 1 minute, I will share. Come back to the PPT there. I will come back to the presentation. I will just come back to the presentation and then. So I think many of you have understood the Arduino IDE. If anyone is having any doubts related to Arduino IDE, you can ask, or otherwise I can move into the other part of our this Arduino programming part. So anyone having any doubts? Okay, then let us move. You can also ask at the ending of that, or you can also post it on the WhatsApp group. So anyone having doubt?
No.
Okay. So before going to the coding part, because I am going to explain you the coding part of the Bluetooth control wheelchair. I just explained you the wheelchair, or you can call it as an motors. You are having a motors there. So I will show you the coding part, how you can control a particular motor by using a mobile app and connecting that motor to via Bluetooth. So before going into that, as I had said you at the starting of the session that as I said, starting of a section that your Arduino board is only capable of working at low voltage levels, right? But if you are using a motor, so if motor may take 10 amps, 15 amps, depending upon the torque and the load that is can capable of taking, so it will take a heavy current. Then what you are going to do? So whenever you are going to use a motor along with the Arduino board, so here you will get an important part that is known as a motor drivers. So depending upon application, there are different types of motor drivers like L298N. I will show you, but you can see on the screen. You can see on the screen. This is the L298N motor driver IC. So apart from that, we are going to have L293D, and then if you are having the motor rating more than that, because these are going to control a motor up to 2 amps, so you can use it easily for a stepper motor or a servo motor. So I think you people know about the stepper and servo motors. So for the stepper motor and servo motor applications, you can use this up to 2 amps. Okay, so but if you have motor, you are using a PMDC motor, which we are normally going to use in our wheelchair applications, right? So there the motor is going to take the current of 10 amps, 15 amps like that. So there I am going to suggest you a motor driver that is MD20A. So this I have written here. This is the MD30A, 20A. The 20A itself represents that it is capable of carrying a current of 20 amps. So you can easily control a motor there. So you can get the complete truth table of that in the description. And then at the end of the presentation, I will give you some websites where you can purchase the Arduino boards. Anyone having any doubt?
Please go ahead. Please go ahead, Sajal.
Okay, sir. Okay, sir. So, there, depending upon your application, you can use the controllers there. So I am going to explain you this particular L298 control motor driver module, how it is going to control the direction of the motors. Because in many of the applications you need the motor there. So you can see here, this is the truth table. So before going to the truth table, let me explain the pins of this motor driver module. Okay. So, because I am explaining first, I had explained the Arduino, and then I explain the motor driver, and then I will explain the coding part, and then I will show you how combining this, how can we control a particular motor there, like wheelchair there. I will show you in a video. So this is a L298 and motor driver IC. So here you can see that these 4 pins, 1, 2, 3, and 4. These are called as an input pins. That means these pins are going to be connected to an Arduino board. From the Arduino board, these pins are going to get the input control signal, because the Arduino is going to give the control signal to this motor driver module. And after getting the control signal, this motor driver module is going to control their motors. So here you can see one set here and one set here. So these two sets. So you are going to connect one motor here and other motor here. So this module, motor driver module, is capable of controlling 2 motors at a time, depending upon the control signal that it is getting from the Arduino board. Like you are going to connect, like let us consider I am connecting motor A here and then motor B here. Okay. And then here these 3 pins here, these are for power supply, right? Like this is an electronic chip. So this needs a 5-volt supply for its operation, right? And we are going to connect the motors there, like one motor B here and motor A here. So these motors need a power supply of 12 volts. Remember that this IC need a power supply of 5 volts, but the motors that we are connecting to this IC, those motors need a power supply of 12 volts at a higher current rate, right? So how we are going to do that? So here you are having 3 pins. This will be 5 volts pin, this will be 12 volts pin, and this will be ground pin. Okay. So you will connect the 5 volts in between these 2 pins, and you are going to connect the 12 volt supply. Take the supply depending upon your motor rating. If your motor is a 1 amp motor, try to take the power supply which can supply a current rating of 1 amp. So, and then how this is going to control it? Like you are having 4 pins, right? IN1, IN2, IN3, and IN4. So let us divide IN1, IN2 into 2 parts. So IN1 and IN2 will be for controlling motor A, which is connected here. IN2 and next IN3, sorry, and IN4. use it for controlling the motor B here. Okay, and then you are also going to have enable pins. This endpoint, this is enable 1 and this is enable 2. So enable A will be for motor A and enable B will be for motor B. Okay, so the first thing that we need to do is enable pin. So if you are going to use 0, that means like as I explained you here, so Arduino is having these different digital pins, and this digital pins is going to give 0 or 1. If you are writing in your code low, so it is going to give 0. If you are going to write 1, it is going to give high. And these analog pins are going to give a signal between 0 to 1, 0, 2, 3. Okay, so I am not, my motor driver IC is going to get connected to these pins. Okay, so when I write low, let us consider I had written low for enable A pin, this pin. Okay, this pin, I will adjust everything. So when I give 0 to this enable A pin, so whatever the input you are going to give, either 1, 1, 1, 0, 0, 0, so the motor is not going to respond anything because you had made the enable pin low. So whenever you are going to make the enable pin 0, whatever the input you are going to give, it is not going to respond. And I think most of you know who have studied the controllers, master slaves there. And then if you give enable pin 1, then you have to come on to the set that what are you going to give at the input pins. Like if you are going to give 0 and 0 here, then the motor will be braked or stopped. And if you are going to give 0 and 1, so the motor will be moved in backward direction, like anti-clockwise direction. And if you are going to give 1 and 0, so the motor the motor A is going to rotate in clockwise or forward direction. And if you are going to give 1 and 1, again the motor is going to get stopped. So similarly, if you are going to make the enable pin B0, whatever they're going to give, the motor is not going to respond. So in this way, right? So in this way, by changing the digital data on the input pins 1, 0 like that, you can control the motor direction. So these are the truth tables which I had explained you. So depending upon these truth tables, you can control the motor direction. So you can see here I have that. So this motor driver is just acting as an intermediate between the motor and my Arduino board. It is receiving the control signals from the Arduino board and it is controlling the motors. So it is just acting as an interfacing board between the motor and the Arduino board there, right? So receiving the signal from Arduino and controlling the motor direction there. So it is acting as a middleman here. Okay, and then this is how we are going to connect here. So this is very clumsy picture here. So I just explain you how you can control a particular motor using the Arduino board. So for controlling it, like I want to control my motor via Bluetooth. So I am going to connect my phone to a Bluetooth device, and then when I click on the forward, my motor will rotate in one direction. When I click on the backward, or when I say forward, it will rotate in forward direction. When I say back, it will rotate in backward direction. So how it is going to happen? So here we are going to have a Bluetooth module here. So this Bluetooth module is going to receive the Bluetooth data from your Android app. At the end, I will give a link of a particular, I will give a link of an website where you can easily, without any coding knowledge, you can design your Android app. I will give you the link of that. And it is a free platform where you can design your app without any coding language, and then you can download it. You can run it on your Android mobile, or you can upload it in the Play Store so that your friends can also download it. So I will show you. I will give you the link at the end of the session. So this is a Bluetooth module. This is going to receive the Bluetooth signal from the Android app, and then it is going to give the signal to the Arduino board. And depending upon the data receiving from the Bluetooth module, this Arduino board is going to give a signal to the L298N or L293D motor driver IC, and this motor driver IC will control the motor direction, whatever the signals it is going to receive from the Arduino board. Okay, so this is how we are going to connect here. So I will stop the slide here. Let us move into the coding part there. So 1 minute. And now again I will go into my Arduino software. So I think now you can see the Arduino software here. So Arduino IDE software. So now I will show you the coding part. So don't think that for coding an Arduino board we require an expertise in the coding. If you don't know any coding, you don't know C, C++ or Java, but you can do the Arduino coding. I will explain you the easy ways. You can do the Arduino coding, you can do the, and you can develop your Android app, and you can do your prototype there. So here I am showing you the coding part of that. You just need to learn some basics of that, very small basics. Uh, so what like that? So remember that in the Arduino board, if you are going to program the Arduino board, like you can see on the screen, you are going to have only two main loops here. Okay, or you can call it as a void here. So one will be void setup and other one will be void loop. Okay, so what you have to remember here is whatever you are going to write under void setup, it is going to run only one time. That means your Arduino board is going to get turned on. Whenever the Arduino board gets turned on, it is going to run the code that is under the void setup, and that's it. It is going to remember that, and after that it is only going to run in between the void loop. It is not going to come out of the void loop. It is going to be inside the void loop. Okay, so void setup will be a setup where it will read that what is this pin, is this pin is output or input, what is this, what is the baud rate that I have to run. So it will read all the data once. After that it will remember those settings and it will go into the void loop part. Okay, so so and whatever the settings you are going to give, you have to give in the void setup, and whatever the main code, that main code should be written in the void loop here. Okay, so before void setup and void loop, if you are having any functions like my pin, I am having a pin that is the second pin of my Arduino, but I don't want to call it as a second pin. I want to call it as a motor one, right? That means I'm going to give a name to my pin. Then you have to define the name, that whether that variable with the name of motor one is going to take a digital data, that means integer data, float value. Float value means the points data, 0.1, 1.1, 2.1, 3.1, or it is going to take a string, that means a word, whatever, that means like forward, back, left, right, like a complete word, what is it going to take, the variable. Okay, so if you are having any variables that you are writing on your board, you have to write them before the void setup. Okay, the Arduino is going to have void setup and void loop, but if you are defining any variable which is on your own, then you have to write it about a void setup. Like here I have written my variable I have written is a void read voice. Okay, so I have written it as read voice, where I am going to get the voice commands from my Android app, because when I say forward, it is going to get into my Arduino board, and the forward command is going to store in this read voice variable. So it is going to store a word, right, as forward, back, left, right, or stop. So it will be a string. So the data function will be string here. Okay, and you can ignore this intk. Okay, there is no need for that, because that also you can execute that. But if you want, you can, let us see. Okay, let us take int k equal to 0. K is a variable, and initially I am loading 0 number in this k. The k is going to take only 0, 1, 2, 3, only numbers, not decimal numbers, not a floating numbers also. Only it is going to take 1, 2, 3 like that. So integers, it is going to take a complete integers. So int k equal to, that means the k variable will going to store the integer, right? Like here the read voice is going to store a string. So I have written the string in front of this. If you are written properly, so it will be in blue color, and k is going to store integer, so it will be int. Initially I am storing 0 here. And then coming on to the void setup. So first, the thing that you need to do in the Arduino coding is you need to define the baud rate, at what baud rate it is going to run. Like 9600, I have said that Arduino Uno will work properly at 9600. So serial begin 9600. That means it is going to take the serial data at a baud rate of 9600. The baud rate means the how many bits by data, how many bits of data it is going to take per second. It is called as a baud rate. So it will be 9600, and then I am going to have 4 pins, right? Because the Arduino is going to give signal to the motor driver IC. As I said to you, that motor driver module is going to have IN1, IN2, IN3, and IN4. And these 4 pins are going to connect to my Arduino, right? So I have going to connect second, third, fourth, and fifth pin of my Arduino to the motor driver, and these pins are going to give the signal to the motor driver, right? That means these pins are going to act as an output. So that's why I have to mention the Arduino that second, third, and fourth pins are output pins. So for defining that, I am using a function as pin mode 2 comma output. That means the second pin will act as an output. Pin mode 3 comma output. But pin mode means pin mode, whenever you are going to write a pin mode, in the bracket write the pin number and then is it acting as an output or input. That's it. Okay, so I had defined all the 4 pins, whether output or input, and then coming on to the while loop, the first thing I need to write is while serial available. That means if the data is available on my Bluetooth, okay, and then if it is available, then that it is readed and it is stored in the C, and then from the C it is readed in the read voice, it is stored in the read voice command. And if the length of the read voice is greater than 0, then that means the first thing it is searching for the any data available, and if the data is available from the Bluetooth, it is storing it in a C, and after storing it in C, it is again storing it in the read voice variable, and then it is going to come into the comparison part. So it is going to use the if else statement. If my read voice length is greater than 0, if the length is greater than 0, that means some data is available. Then what it should do? It should again have a if command where it will if the data that in read voice is forward, whether it is forward, if it is forward, then make 2 and 4th pin high and the remaining pins low. That means IN1 and IN3 are going to high and IN2 and IN4 are going to low. My 2 motors are rotating in forward direction. And if read voice is the data that had come in via my Bluetooth is backward, then 2 will be low, 3 will be high, 4 will be low, 5 will be high. That means what happens? IN2 and IN4 will be high and remaining will be low, so that my motor will rotate in backward direction. And then if it is left, then one side motor should be off and other side motor should be on. So which side should be on and which side should be off? If I want to rotate left, then my left side motor should be off and my right side motor should be on. Then only my motor or whatever the robot I am having, it will rotate in left direction. Depending upon that, we are going to code it. Okay, so this is the complete coding part. So same is going to repeat for the left, for the right, for the stop, like that. So for the stop, everything will be low. 2, 3, 4, 5, everything will be low, so that my motor will be in stop condition. Okay, so this is the coding part here. So we have less time, so let us quickly move into the how this is going to work. So 1 minute. So now I will show you the project that we have done it in our college, that I had done under the supervision of R.P. Tiwari sir. I had done voice and EEG based smart wheelchair, or we had named it as voice and thought control wheelchair, but we had interfaced our wheelchair via EEG and also voice commands, so that we can know that like if whatever the powered wheelchairs that are available in the market, those will be controlled by joystick, right? But if a person which is having complete body paralysis, who cannot move his hand or legs, how he can move, the mobility will be difficult for him, right? So for that we had designed the voice and brain control wheelchair, where he can control the direction of, he can move the wheelchair by his voice commands, right? If he can give voice like forward, back, left, right, and stop. And if he can say, if he's not able to talk also, then depending upon his brain signal, the wheelchair can be moved, and depending upon, but that the brain controlling is in process. But what we had done is, depending upon the eye blinking, if he is going to blink his eye, so there will be variation in the brain's EEG of his EEG. Then depending upon the EEG signals, the wheelchair is going to move in forward, back, like that. So 1 minute. So this is the wheelchair that we have developed here. So we have named it as voice and EEG based smart wheelchair, and we can also call it as an integrated wheelchair because it is having many options. It is having the voice option, it is having the EEG option, and you can also add the joystick here. Okay, so this is one of our friends who is operating this. So here you can see at the top on his head. On our head, you can see this is the EEG headset, right? This is the EEG headset. So it is a NeuroSky MindWave headset. So if you go into the NeuroSky website, you can see the headset there. So it is a 12-channel EEG, which is going to capture the EEG signals from the human subject, and then it is capable of transmitting that EEG data wirelessly. So you can collect. So you can see here, no voice has been connected to her. So it is going to just capture the EEG signal from her scalp, and then it is transferring it wirelessly. It is going, you are going to get a dongle with it. You are going to connect the dongle to this laptop, and it is going to get the signal in this laptop. And after getting the signal in this laptop, we are going to process the signal, right? So how we are going to do this? So you can see here, this is one of the part of that, like the user has blinked his eye slowly. That means he has closed the eye slowly and then opened that. So this is the raw signal. So we had processed the signal in the MATLAB, like the JK has told in the previous session. So we had processed that in the MATLAB. So how we are going to process it? We had written a script, and then we are also using the MATLAB blocks also. Okay. And what the interesting thing that we had done here is we had interfaced the Arduino board. I had explained the Arduino board you, right? So what we had done here is we had interfaced the Arduino with this MATLAB. So whatever the signal processed in the MATLAB, it is going to as a control signal to the Arduino board, and then Arduino is going to control the motors there. So we had done that in a MATLAB. Whenever you are going to, if you are having a MATLAB version of 2013 and above, 13, 16, 18, 19 or 20, so there you are going to get an add-on options. In the add-on, you can add the Arduino boards. Add-on, you can add the Arduino board, Raspberry Pi boards. So you can add the boards, and then you are going to get the blocks there. Using those blocks, you can easily control the Arduino. You can transfer the commands from the MATLAB to the Arduino board. Okay. So what we had done, initially we had get the signal, right? The EEG headset had transmitted the signal to my laptop, and then we had taken it into MATLAB. So this is the raw EEG signal, and then we had filtered it. Like here we are having some distortion in the wave, and here we are having some distortion. So we had filtered it. This is my filtered EEG waveform, and then we had extract the peaks from it. Okay, because whenever we are going to take the eye blinking pattern, so depending upon the eye blinking pattern, so the peaks of the, that means the amplitude of the EEG is going to get varied. So we are capturing the peaks. So as I had explained you at the top, I had mentioned you. So for the long blinking, so we had used the long blinking for forward. If the user blinks it high for a long time, so the amplitude will be between 50 to 145 microvolts. Remember that as we are capturing the EEG signal from the scalp, so you are going to get the EEG amplitude in only microvolts. You are not going to get the EEG wave in a millivolts, because we are not connecting the electrodes directly on the brain. We are connecting on the scalp. So you are going to get the voltage in a microvolts range. Okay. So we had processed it, and then we had extracted the peaks there. Okay. And then these peaks had been given as a signal to the Arduino board, and I had written a command like, if my signal that I am receiving from the MATLAB is greater than this particular peak, then try to rotate my motor in the forward direction. So depending upon that, it is going to rotate. So this is the this is at the time of testing, so it is looking somewhat like that. So after that, we had designed a complete PCB. We had embedded all this on the PCB. We are using a battery here, and we are using some relay switches. But later on, we have replaced these relay switches with the complete module. Okay, and here I am using two controllers. So this is my Raspberry Pi, and this is my Arduino board. So just concentrate on this Arduino board, because this is going to get the EEG signals from the MATLAB, and then it is going to give the control signal to this motor driver IC, and then this motor driver IC is going to control the motors. So we are using the PMDC motors for the two wheels of the wheelchair, and it is going to control the direction of that. So I will try to, so you can see here. So this is at the time of testing. So you can see both the wheels are rotating in forward direction. So I had given the voice commands there. So easy as not shown. So when I given the backward, you can see though the wheels are rotating in backward direction. And when I give right left, so you can see that my left side motor had been stopped and right side had been rotated. When it's given right, so this is rotating and this will stop, so that my wheelchair will rotate. When I given stop, all the motors are being stopped. Okay. So this is one of the thing that we have developed, and still the work is going on, because we are concentrating to develop a complete thought process, so that whenever the user is going to think on that, the wheelchair has to move. We have just given some EEG and voice interface, like voice, as I said to you, we are using the Arduino. When I'm in a mobile app, whenever I give forward, the command is going via Bluetooth to the Arduino board, and then the motor is going to control. And EEG signal is capturing from this NeuroSky Mindwave. You can get these details of this NeuroSky Mindwave in their website, NeuroSky. Spelling will be NEUROSKY, NeuroSky. and there are many other companies which are manufacturing the easy waves. So we have preferred it because these are used for treating the children who are having cerebral palsy problem. So there we are taken it from there. So you can also have different types. You can go through that. And the other thing that we have developed in our lab is we are using actuators for biorobotic application, mainly for lower limb prosthesis device. Like here we had taken an actuator and we are going to control the motion like plantar flexion and dorsiflexion of the ankle joint, so that the person can move as a normal person, can walk as a normal person, where we are going to control the plantar flexion or dorsiflexion movement of the ankle by using a pneumatic muscle there. Like we are going to have two muscles, right? One will be in the posterior and one will be in the anterior. So these, because of the contraction of these two muscles, our ankle is going to move in the anterior and posterior directions, right? So we have replicated that. We have replicated the muscles operation there by using an artificial muscle, which is a pneumatic muscle, PAM. We can call it as a PAM, which is pneumatic actuated muscle. Okay, so you can see here, this is the PAM that we had used, and this is has been made by the Festo company. So I have a video also how this PAM is working as a muscle. So this is going to act similar as a muscle. Whenever it is going to compress, so the diameter or the size of this PAM is going to increase, and whenever it is going to come into the normal size, the size of this is going to get reduced. So this is going to work as an actual muscle, right? So how we had controlled it, okay? On the left side, you can see here, this is our setup. Okay, so initially we are testing it by placing some weight here. So we had tested from a weight range of 2 to 6 kgs, and we are also gone up to 8 kgs. So for this PAM is working effectively up to 8 kgs load, and normally the foot is not going to have that much weight. So we are also tested at a range of 0 to 2 kgs because okay, so this is the PAM, which is PAM actuator, and then we have used ultrasonic sensor. So the reason why we have used the ultrasonic sensor is, here we are trying to see how much variation in the length is going to happen here. So this is my ultrasonic sensor, and we have placed a plate here at the ending of the PAM. So this sensor is going to measure the length of the PAM, right? And this is the weight that we had placed. And here we are having a compressor, 8 compressor. This is the setup, and you can see here, this is my controller part. So how we had controlled it? So we had again used the same Arduino Uno. I am showing you the Arduino Uno because I want to make you know that we can do the prototyping or testing very easily and very fastly by using the Arduino board. So here we are using an Arduino Uno board, and then we are having a motor driver here. Okay, so the reason why we are using the motor driver here, I will explain you. Okay, so here we are having a proportional pressure regulator valve, and then this is a regulator, pressure regulator. Okay, so this, now let us see how the complete circuit is going to work here. So from the compressor, this pressure regulator is going to get the pressure. So the pressure may be more, so it is going to decrease the pressure to 6 bar, the maximum range of 6 bar. Okay, and then the 6 bar pressure is going to come to this pressure valve, regulator valve. Okay, and this is an electronically controlled sorry, and this is an electronically controlled pressure regulator valve, which is going to get the signal from this Arduino board. Okay, so this needs a voltage of 0 to 12 volts, and Arduino is capable of giving a voltage of, as I said to you, 0 to 5 volts. So this driver is used for giving the additional supply. So Arduino is going to give the PWM signal, which is going to vary between 0 to 255. Okay, so this PWM signal will be fed as an input to this regulator valve, and depending upon, if you are going to give 0, it is going to give a 0 bar pressure at this output, because input it is getting a 6 bar pressure, and the output it is going to get a 0 to 6 bar varying pressure. So at the input it is a fixed pressure, at the output it is going to get some varied pressure, which we can vary easily between 0 to 6 bar, because my PAM, which I have used in my application, is capable of operating at the pressure of 0 to 6 bar. Okay, so initially we are getting 6 bar, and then after getting a signal, if you are going to give 0, okay, it is going to give the 0 bar pressure at output. If you are going to give 255, which is the maximum, so it is going to give 6 bar. Okay, so and then this pressure will be fed to the PAM. You are having a nozzle here, and the pressure will enter into the nozzle and then go into the PAM. If you are going to give the zero pressure, so initially the PAM is going to have a length of 140 mm. Okay, 140 mm. So when you are going to give the zero bar, it will not going to do anything. It will be 140 mm length. Okay, so if you are going to give the 3 bar pressure, if you vary the voltage here, so the pressure coming to this PAM is going to vary. So let us consider the pressure that it is getting is 3 bar. So what happens? This length will increase from 140 to 145 mm. And then if you are going to increase it more, it is going to get 6 bar, then it is going to increase the length of 150 mm. So depending upon the pressure that it is getting, the length of the PAM is going to vary similar to an muzzle, right? And then we can use this PAM and in our robotic application where we want to move the ankle joint or whatever the joint you are having just by varying the length of this PAM. The PAM length will be varied because of the pressure, and the pressure can be varied by giving an signal from the Arduino board to this pressure regulator valve. Okay, so here I am having a video. So you can see here it is varying in 10 mm range, so it is not visible that much. You can see here it is going down and going up. So you can have, we are also showing here. So this is the Arduino board that we are having, and then here we are having a motor driver, and this is a circuit of 12 volts which we had designed, and then this is an pressure where you can see the variation of the pressure here, and this varying because of the signal that it is getting. Okay, and then this is the pressure controller, and then here we are having a compressor at the side. Okay, so these are the things that we had done. Apart from that, we had done many things, but because of the time constraint, I am not going to explain everything here. And then at the COVID-19 time, so at the COVID-19 also we had worked to develop some devices, like as R.P. Tiwari sir had said that at the starting that we had developed a thermal scanner. So you can see here, this is the thermal scanner which is going to get, we are going to file a patent for that, and it is going to, it will be placed at one place. And we are also designing a mounting device, but I am not showing it here. So it will be placed at one place. If a user going to stand in front of it, first it will measure the height of the person, which is be done by the mounting device, and then the height will be adjusted. And when this control, this is the IR thermometer. When it comes in front of the head, it is going to measure the temperature, and it is going to transmit it wirelessly to a mobile app, which is at a distance of 8 meters. So it will reduce the risk of the person who is going to measure the temperature or who is performing the thermal screening at the entrance of the gate, because we have to consider the health of our security guards also. So here he can stand at a distance of 8 meters, and if you come at the entrance, you will stand in front of the device. It will measure your temperature and transmit the data wirelessly to a mobile app. And this is the other project which we had developed for during the COVID-19, which is a wireless pulse oximeter. So this is a normal pulse oximeter. You are going to place the finger here. Okay. After placing the finger here, this is going to measure the pulse oxygen and heartbeat, and then it is going to upload this data into a website or a server, secured web server, and from there the doctor will log in and he can check your pulse oxygen and your heartbeat at a regular basis, because at the COVID-19 the pulse oxygen level is one of the important factors that we have to consider during the coronavirus, right? So who are having a home isolation, they can use this device, and the doctor can monitor the person's health from hospital by just logging into a server. This is an IoT device. Okay, and this is both of the devices are very cost effective. If you are going to get only this, you can get it under 1,000 rupees, and this is also you can get it under 1,200 rupees. Okay, so these are very cost effective, because a normal pulse oximeter you are going to get at 800 rupees. This is advanced from that, and you are going to get it under 1,200, because at the time of fabrication we have got 1,200, but if you are going to manufacture in a bulk, you are going to get the rate down. So these are and we are also working on some other projects during the COVID-19 because our institute also going to get open. If we get open, so we are also going to work on various other projects. So this is one of my website, which is circuitata.in. So I use it to conduct some workshops on my own. So if you are interested to attend any workshops like app development or Arduino or IoT. So you can go into the website and you can register there. And then this is my company's website, which is Henixia Private Limited, which is a new startup. And we are working on IoT devices, and maybe by next 2021 we are going to launch a product there. And then these are my mail. If you are having any queries after the session, also you can mail it on my on to these two. You can mail it on info@henixia, or you can also mail it on sazal@henixia.com. So thank you. So if you are having any doubts regarding the programming part of Arduino or anything else, you can ask. Thank you.
Any questions, please? Any questions, please? Thank you, Mr. Sajal, for such a nice presentation. Thank you
Sir.
so much. Thank you so much. So
Thank you, sir.
tomorrow we have 14th and 15th session, and then there will be a quiz at 3 p.m. So I would request all the participants to please join first two sessions at 9:30, and the second session is at 11:30. So please join tomorrow at 9:30. Thank you.